solidarity and all of that, you have to understand the control-free case a bit better. And that's why this linear progression of the course, that, do Markov models and controlled Markov models, then reinforcement learning. And so we're being linear. And again, the homework probably won't be, but the lecture will be. So really, basically, this is it. We're going to start. So again, I claim to you that every Markov chain has this representation. I can write the new state as some function of the old state and noise and disturbance, where this sequence is independent and identically distributed. All right. So that, to me, that's a Markov chain. I swear to God, you've got to believe me that I've been teaching this course for 1,000,000 years, and every time I say, please believe me, maybe not the first time, if you don't memorize the notation I'm giving you right now, you will fail the course. But 3 of you are going to ignore me. It's going to be April, and you say, but Professor Mine, the notation was so hard. And I'll say, well, there were 4 things I asked you to memorize. So this is the loudest I've ever said it. Well, maybe, did I say it that loud before? You were there. No, okay. I mean, it's one thing to write down, okay? So you saw all these conditional expectations coming about. Like, so let's suppose, so X is in some state space, Xn, I'm calling it X, and whatever you're comfortable with, it could be Euclidean space, it could be a finite set, whatever you're comfortable with, I'm happy. I'll probably restrict to a countable state space, just to make some of the notation simpler. You saw all these conditional expectations I was writing a moment ago. We really need it over and over and over again. Conditional, given some function. I'll call it capital H just to make it very different from everything else. It's something like a value function. Or it's gonna be something like what came up in these dynamic programming equations. You saw I had the expectation of H of x27, given x26 equals x. That came up over and over and over again, right? And we know what that is because we know what x27 is. It's right there. N. That doesn't matter. I'm emphasizing the fact that under this IID assumption, it doesn't matter what n I put in here. Xn is x, so I'm plugging in xn equals x, right? And then this n plus 1 is independent of xn, so I just take an expectation. And I might as well just take 1 here, instead of 26, 1. Right? Now, here's a thing that 3 of you will refuse to memorize. That I'm going to denote this as taking P, multiplying by H, and evaluating it at X. Okay, that looks really weird there. Where did this thing come from? P is the transition matrix kernel. It's called, the transition matrix you've all seen before. You call it a kernel because it's some asymmetry. It starts off being defined like this. So I brought this up last time. I just didn't give the notation. So you start off defining this transition kernel, which is completely basic. This thing, in your flashcards or your one page of notes before midterm, you're going to make sure that's on there, what a transition kernel is. And I'm going to try to convince you that this notation is really nice and convenient. Rather than having to write down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 symbols. Typically I'll just write down 2, because I won't bother to tell you x. I've got a new function. Given h, I've got ph. And it's important because it comes up in every single lecture of the course until April. When we get to optimal control, we'll have a pH. It'll be controlled. When we get to reinforcement learning, we're going to try to approximate those Bellman equations. And I don't want to have to keep on writing that out. I don't have enough blackboard space. All right? Now, what's the motivation? In the finite state space case, let's say there's capital N states, right? And then that transition kernel really is a matrix, So the probability of going from I to J I'm sorry, this often confuses people. Again, transition kernel is a function of two variables. It's a function of an initial state x, so I look at any possible state, and any subset of x. Of course, there are restrictions there. We'll talk about those restrictions later. Okay? So it's a function of two variables. It's not symmetric like a transition matrix. I don't have to worry about sets anymore. I can just look at every possible individual state. And what is the suppose I have H mapping X to R. H is just a function on a finite alphabet. Give me 1, I have H of 1, it's a real number. 2, H of 2 is a real number. It's a vector, basically. Think of the states as indices. H of 1, H of 2, H of 3, it's just indices. And what's the conditional expectation? I'll put an I there instead of X, because, just to emphasize the integers. Well, it's equal to, I sum all possible values I could end up at it in one hop, and look at the probabilities. See, I'm looking at the probability that xn plus 1 equals j for every j, and I sum them up. That's an expectation, right? Do you agree? So doesn't that look like matrix vector multiplication to you? Wouldn't you write that as pH evaluated I? If you took a matrix class, then memorize it. Why will some of you not memorize that? Because I'm going to use it, and you'll be lost if you don't memorize it. So whenever you see me write pH, it's shorthand for a big, long, messy thing. Okay, and I insist on you memorizing this. I don't know why you refuse to. I don't know which one of you it is, but you. Probably, I'll bet it's a person not sitting here. Yeah. Because all of you feel the tension, and you won't forget. But the person who's not here, okay. That's why we should put these lectures online, maybe. I don't know. All right. So now, I swear to God, I'm going to try to minimize this, but one more. There really won't be many of these. Another one. This DH is just the expectation of the increments, all right? And so h of xn, conditional expectation of that given n equals x is just h of x. And this is just what we had before. So this really is nothing more than ph at x minus h of x. And so this d is nothing but p minus I. All right, there's two. And I don't think there'll be more than 5 weird symbols like this. All right. Now, why does this come up? It's because all the time we're looking at different expectation of increments like that. It came up in those Bellman equations, if you take a look at it. Recall. This was our Bellman equation. If you go back to where we were before, in the case where I had a cost function that didn't depend on u, I was minimizing overall u here, and I get a feedback policy, state feedback policy. So basically here I'm just replacing the minimum by just plugging in the optimal policy there. Okay, and you can see I've got a conditional. This is my p8 star, and there is my 8 star. So you can write this as what? I can bring the c to the left-hand side. And then bring this over here, and I have exactly this difference. And the star there is just the fact that I'm plugging in, I'm looking at this difference operator under the optimal policy. So if I take u to be this optimal policy that you get through all these dynamic programming arguments, I get a Markov chain. And so I'll get some sort of difference operator there. And all I did is I took that to the right-hand side, and that's it. So you can see it'd be really useful to have this throughout. The other reason for introducing it is that I'm going to develop Lyapunov theory and explain it first in continuous time where the geometry is much more clear and beautiful. And then instead of a difference operator, you have a differential operator, and they're exactly analogous. And the solidarity will become clear as we go along because of that. All right? Okay.
So
Yeah.
So P is not an actual matrix.
No, that's the thing is that
It's just that
I'm generalizing the finite state space notation to general state spaces. And again, it's because you get such compact expressions, and there's other reasons as well. You'll see it's really, really useful. I just can't, I tried to drop it once because people are so averse to accepting it, and I just give up. I mean, I can't drop it.
Is this like universally accepted?
Yes. Oh, yeah. I mean, in the Markov chain literature, it's what people use, and statistics. I mean, like MCMC and the conference across the street. You'll see a pH. Actually, you'll see a DH everywhere. But instead of a difference operator, it's a stochastic differential operator. It's because they look at stochastic differential equations in a lot of the work. Yeah, absolutely universally accepted. Not in computer science. In computer science, it's not. But in Markov theory and and I'll see right now that I'm surprised it's not more. This isn't used more in optimal control texts like deterministic, as I'll show you in a second. So. So the whole thing is going to be stability in something called Lyapunov functions, which are a generalization of this equality I've just written down. Okay? So there's basically, this is like the basic stability condition I've got some cost function. It doesn't have to be, but typically we'll interpret it as a cost function. It might be some big function that dominates the cost function of interest. We search for a function v. Also positive valued, such that dv is less than or equal to minus c plus a constant. And it sounds pretty, this is actually called Poisson's equation. Any physicists out there? I don't know. So that's like the Laplacian, and that's the forcing function for Poisson's equation. So there's a Poisson's equation in physics, and this is a generalization, and this is all over the place in mathematics and control and everywhere. And so we'll call this a Poisson inequality. And I'm not going to give you a theorem right now. I'm going to say that basically if we want to get performance bounds, like what's the average cost? We can't compute it. What's a bound? Well, it's bounded by eta bar. And maybe we can get a bunch of approximations and play with them. And basically, anyway, that's the goal. All right. And once we get these Lyapunov functions, all sorts of fun things we can do with them. Not just say the Markov chain is stable in some sense, but we'll be able to do other things as well. It'll help us in simulation, all sorts of things. All right. So, how far will we go? So, just like in the overview I gave in the first hour, it's so much easier to talk about deterministic systems first. So for this, I erased my Markov chain. It's going to be of this form. I've got d dt little x of t is equal to some function of x of t. So this f of x of t could be like the mean behavior. You know, one possibility is that f of x is what I would call f bar of x equals the expectation of the original f of x and n. All right, so this is how you create these fluid models in general. Oh, wait, minus x. Maybe like that. So I shouldn't do that. So remember with the queuing model, I looked at the increments of the process, and I had something on the right-hand side. For the queuing models, the x is canceled. I only had a function of an input u and noise. Okay, so this OD model for a given, I start with the Markov model, all right, and I look at this difference, and I look at the mean the mean of the increments, the conditional mean of the increments. And I use that to define my f. I know there's a conflict of notation here. I'm sorry about that. I'll put a prime there maybe, just to make it different. But I've got a Markov. I start off with a Markov chain, and I look at the mean dynamics. That's one thing you could do. That's what I did with the queuing model. Okay, so I'm not saying we're going to do that. I'm just saying that's what we just did in the MM1Q. We start with a discrete model. We looked at the fluid. And how many of you have seen this sort of thing? You know, you're supposed to have some exposure to control in the past or something. You've looked at dynamical systems. You have. Yeah. All right. And stability of them. Yeah. Kind of shy. Okay. We need some assumptions. I'm going to take this in 2 dimensions. Why 2? Because the blackboard is 2-dimensional. And I'm going to assume there's an equilibrium. All right, so saying that there's a state for which f of x star equals 0, I mean that's 0, 0 just here. If I plug in x star here, I get 0, which means the derivative is 0, which means I'm stuck there. So it's called a stationary point. Oh, this was maybe just confusing. And that's the question, the basic question in stability theory for, one basic question, stability theory for deterministic systems. And the way it's answered is through Lyapunov theory. and it's just like this. All right, so we have to figure out, there's a D involved, which is just a different D, and there's no eta bar, and that's it. Yeah.
I'm sorry, what is that fx star equal to?
Oh, well, yeah. Once I'm writing this longhand, I've got a dynamical system here. So if x is in R2, f beta value is in R2. All right. So if I write fx star equals 0 from the context, I mean 0, 0. Okay. All right. So what's the Lyapunov function? Also, sorry, R2. There's so many definitions, by the way. This is just one. So again, I just said there's an R plus there. It takes values in R plus. I'll just write it down again. It's non-negative valued. And it has a continuous derivative. Okay, so the gradient's just the vector of partials. And secondly, it's coercive. So if you look at large states, V gets big, and it gets bigger and bigger and bigger. So this is a particular class of Lyapunov functions tailored to fit with Markov theory later on. Okay, so it's not maybe the first thing you'd learn in a dynamical systems course. There's a third thing, which is the important thing. So I've got a solution to this differential equation, and I'm not at that equilibrium, a stationary point. Then the derivative with respect to time of v of x of t is less than 0. And so I could sort of think of that as my cost function. It's something negative. I could define this to be minus c of x of t, if you like. Yeah. I'll just put in parentheses there. So this inequality is just sort of a softer version of something strict like this, where I have a cost function I really care about, and I want to have a drift which is less than my cost function plus a constant. This is just fluffier. There's no cost function involved. We will stick one in a bit. We're going to strengthen this as we go forward. Now, we still have the chain rule, right? Actually, first of all, why do I put in this assumption? Just to make sure you're all awake.
Star b should be 0.
Yes, okay. So if we let x of t be x star, then x of t would be x star forever, and this derivative would then, of course, be 0. So first of all, what is this? We have the chain rule. It's the gradient of v dotted with x dot. Oh, I should leave the t. Okay, that's the chain rule for functions, in this class. And again, just like we were discussing before, we have a formula for the derivative. It's just f of x. So this, crucial thing is the same as saying that dv of x is less than 0 if x is not equal to 0, where now instead of a difference operator, I have a differential operator. Where now dv is just equal to that. And normally I get rid of the x's. dv equals grad v dotted with f. Just to keep things simple. All right. So I define d for discrete time Markov chains as a difference operator. If I was going to generalize that, translate that to continuous time, this derivative would be the natural extension. All right, and that derivative by the chain rule is just a dot product like that. So this is the definition for continuous time. And deterministic. If this was continuous time with noise, you would have a different expression. All right. Okay, so here I've got dv. These cost functions that could typically be coercive as well. They're going to blow up for large x. So here we would have dv for this difference operator is negative for large x outside of some compact bounded set. And here we're asking for, that's 0, x star. And here we're asking for, for this to be negative everywhere except for at this one point. Yep.
So with our cost function, if we satisfy the Poisson inequality, what does that say?
Yeah, we're going to get to that. See, what I'm saying is that there's some machinery we want to develop to understand stability and its relation to Poisson's inequality and Poisson's equation, and that is a building block we need for optimal control. But first it's so much easier in continuous time, and it's so much geometry that we lose in discrete time. So it's much nicer to go through and explain in continuous time first. So it won't be till next week that we can get into this.
Yeah.
Yeah.
Question.
Yeah.
So I guess it's pretty common to do sort of control design in Lyapunov functions.
Yep.
And so if you were to do that, can try and connect it back to perhaps you're minimizing a certain cost function. Because here we have a cost function and there's an inequality, and this is going to somehow give us a stability result.
Yeah.
Whereas typically in maybe some control design, you would do that to ensure that you get stability, but you don't really care too much about optimality or minimizing the cost function at all. But is there a connection?
Oh, yeah.
Innately, we are minimizing. There is a cost function that we are minimizing that would come out of the stability analysis.
Well, yeah, we'll get to that. There's a very positive. It's called inverse dynamic programming, and we're going to dive right into that. I would say by early March, or that's spring break. So right before after spring break. Yeah, so absolutely. This, I mean, I can't say it now, but yeah, inverse dynamic programming. It will be. It's hiding right there. Let's see. But all right. So I say this geometry, beautiful geometry. Where is it? So I can kill that. So you pick up any book on stability of dynamical systems, they're going to take your R2. Remember I said that X star is an R2, and that's because we're in a blackboard. Unfortunately, now I need 3 dimensions because I've got my, my X star sitting here, and I've got this function here. I need another axis. You know, like that. And what this is saying is that over here in R2, it's going to confuse me. Over here in R2, in this x of 0, I've got this process buzzing around. You can't see what's going on. But if you go and lift this thing up here, you're going downhill. That's the first thing. You know, v of x of t is decreasing, which means you're falling down this bowl downwards. You know, I'm sort of imagining v being a quadratic function of x here. All right? Another way of saying this is that I've got this dot product is negative. Where'd it go? Yeah. I've got this is always negative. That's a vector. That's a vector. The dot product is negative. They're pointing in, you know, they're not aligned. They're pointing like that. You know. So that's the 3D view. (2D) is just to go back to the plane, put down x star, and write down x at a particular